Hello and welcome to today's lesson on the laws of equivalence. So, logical equivalences. In this lesson we will discover some of the rules for algebra also work for logic. Double negation. From algebra we have the following property. The negative of x is equal to x. This is sometimes called the double negative property. If we have two negatives, they cancel each other out. In logic, a similar property applies. If I have the negation of p, that is equivalent to the statement p. So, the two negations cancel out. The following truth table shows that that is indeed equivalent. So if I have statement p is true, if I negate that, it becomes a false, and if I negate this, it becomes a true again, back to its original value. If p is false and I negate it, it becomes a true, and if I negate that, it becomes a false, back to its original value. So this truth table verifies that the double negation rule does indeed apply. Also from algebra, we have commutative properties. We have a commutative property of addition that says a plus b is equal to b plus a, and one for multiplication. A times b is equal to b times a. In logic, we also have commutative properties. So, p ANDed with q, that is equivalent to q ANDed with p. P ORed with q is equivalent to q ORed with p. And p if and only if q is equivalent to q if and only if p. So, these statements are equivalent. So if you have an AND statement, an OR statement, or an if and only if statement, you can reverse the order and get an equivalent statement. Also from algebra, we have associative properties. So we have associative property for addition, or in parentheses a plus b plus c is equal to a plus b plus c in parentheses. We also have it for multiplication. A times b in parentheses times a c, that's equal to a times b plus c in parentheses. In logic, we also have associative properties. So if I have AND statements, p ANDed with q in parentheses ANDed with r is equivalent to p ANDed with, in parentheses, q ANDed with r. The same thing also applies with my OR statement. P OR q in parentheses ORed with r is equivalent to p ORed with q OR r in parentheses. Let's take a look at our distributive property. In algebra, we have a distributive property of multiplication across addition. So if I have a times b plus c, if I distribute my a through, I get a times b plus a times c. In logic, we also have distributive properties. So this first one, I'm going to be distributing this OR statement across my AND statement. So I've got p ORed with, in parentheses, q and r. So that's going to be p ORed with q ANDed with p ORed with r. So I did p ORed with the first one, p ORed with the second one, and there's an AND between those two groups. I can do the same thing if it's in the reverse direction. So if I have p ANDed with q or r. So that's going to be p ANDed with q, ORed with p ANDed with r. So we also have distributive properties for logic. We also have something called De Morgan's laws. So if I have the negation of p and q in parentheses, that's equivalent to not p ORed with not q. Also, if I have the negation of p ORed with q in parentheses, that's equivalent to not p ANDed with not q. So De Morgan's law is a rule for distributing a negation through parentheses. When a negation is distributed into a parentheses, your conjunction statements, your AND statements, become disjunctions. Your ANDs become ORs. Your disjunction statements, your OR statements, become conjunctions, become AND statements. Alright, let's take a look at the contrapositive rule. So if I have the conditional if P then Q, that is equivalent to its contrapositive, which is if not Q, then not if not Q, then not P. So the contrapositive of a conditional is equivalent to the conditional. Rules for implication. If I have the statement if P then Q, that's equivalent to the statement not P ORed with Q. Also, if I have the statement if P then Q, that's equivalent to the negation of, in parentheses, P ANDed with not Q. So these two rules enable us to convert an if-then statement into disjunctions, that first statement, or we can convert them to conjunctions, which is the bottom one. Now this truth table verifies this first rule to show that indeed they are equivalent. So my input values for P and Q, my conditional for if P then Q, that's going to be true, false, true, true. Over here I'm negating my P column. Negating my P column gives me false, false, true, true. Here's my Q column. So now I'm going to do my not P ORed with Q. So false ORed with true is true. False ORed with false is false. True ORed with true is true. And true ORed with false is true. So this column here for my not P or Q is exactly the same as my conditional. So I verified that these two statements are indeed equivalent. All right, let's take a look at the alternate definition of the biconditional. The biconditional statement, P if and only if Q, this is equivalent to the statement if P then Q and if Q then P. So this statement on the right, if P then Q and if Q then P, this gives us the exact same set of truth values as our biconditional. Idempotent laws. If you AND a statement with itself, then you get exactly the same truth values as that statement. If you OR a statement with itself, then you get the exact same truth values as that statement. All right, identities. If I have P ORed with a false statement. Now, if you remember, the only time an OR statement can be false is if they are both false. So P ORed with a false statement, that's going to be equivalent to P. So if P happens to be true, then the OR statement is true. If P happens to be false, then the OR statement is false. Here I have P ORed with a true statement. Now, an OR statement is true if any of them are true. So this statement is always true. A true statement ORed with anything is a true statement. If I have P ANDed with the true statement, well, the only time the AND statement is true is if they are both true. So if P is true, the AND statement is true. If P is false, then the AND statement is false. So P ANDed with the true statement is equivalent to the statement P. And on our last identity, P ANDed with a false statement. Well, the only time an AND statement can be true is if they are both true at the same time. So since one of these are false, ANDing it with anything gives me a false statement. Alright, let's take a look at these rules called the negation rules. So if I take P and I OR that with not P, P ORed with not P, that is a statement that is always true. And if I do P ANDed with not P, that statement is always false. Alright, so we're going to see a few examples, and in the following examples we are going to be using the double negation property, De Morgan's law, and the implication rules to rewrite logic statements. So let's take a look at the following. Alright, looking at the following here. Example 1 says, rewrite the following logic statement so that it contains only negations and conjunctions, your AND statements. So that means this if-then statement, I want to turn that into an AND statement. And this second if-then statement, I want to turn that into an AND statement. So we're going to use the rule for implication to turn those arrow statements into AND statements. So let's scroll back up here to the top, or near the top. There we are. So our implication rule. So this top one turns into an OR statement, the bottom one turns it into an AND statement. So if I have if P, then Q, that is equivalent to the negation of, open parentheses, the first one, ANDed with the negation of the second one. So I've got to do the first one, ANDed with the negation of the second, all in parentheses with the negation in front. So let's move down there and then try to apply that to our problem. So we're going to have to do a negation of this P ANDed with a not Q. So there it gives me the negation of this P ANDed with a not Q. We now need to do the same thing for the second statement. So I've got to have the negation of, oh, there's my negation of, and then in parentheses I've got to have this first statement Q ANDed with the negation of the second statement, which is not P. So we have taken that statement, if P then Q, and if Q then P, and we've rewritten this into a statement that has only negations and AND statements. Example number 2. So I have the statement, if P then not Q, and we want to rewrite this using only negations and disjunctions. That's my OR statement. So if I go back up to my rule for implication, to convert an arrow statement to an OR statement, I have to negate the front one and then keep the second one the same. Negate the front one and keep the second one the same. So, turning this if-then statement into an OR statement, I negate the front one, so this P becomes a not P, and I keep the second one the same. So if P, then not Q, that's the same thing as saying not P or not Q. Alright, our last example here. Rewrite the following logic statement so that it contains only negations and disjunctions. So I have the negation of, open parentheses, P ANDed with not Q. So here we're going to apply De Morgan's laws. So applying De Morgan's laws, I distribute my negation through. That gives me not P. My AND turns into an OR, and I get negation of Q. And now I'm going to apply my double negation property, and that gives me the negation of P ORed with Q. So thank you for watching this lesson, and I hope to see you next time.